Well, now that we've got all that background information down, we can start talking about what are called the quantum numbers. And the quantum numbers are just a way for us to figure out where these electrons are, which area of probability they're residing in. Remember, the Heisenberg uncertainty principle says we can't really know exactly where they are, but knowing enough about them, using that equation, solving that Heisenberg-Schrödinger equation, we can find out some information about them. The first bit of information we want to know is what energy level are they in. And this is the very most basic. This corresponds exactly to Niels Bohr's levels. He had orbits, circles around the nucleus. We know it's not like that anymore, but the idea was right, that there are energy levels that these are in. Energy level 1, energy level 2, energy level 3, and that's the principal quantum number, is the energy level that the electrons are in, or are most likely to be found in. I'm not going to keep saying that. I'll just say what they're in. Remember, that just means where they're most likely to be found. So that's given the symbol lowercase n, the principal quantum number. Principal meaning first or most important. The higher the number, the farther it is from the nucleus, although the distance between 1 and 2 is not the same as the distance between 2 and 3. All right? They get closer together the farther you go out. And for hydrogen, the distance between 1 and 2 is different than for helium and different for carbon. So without actually looking at the spectra and measuring the energy of the photons that come off of there, we can't know what that distance is just by calculation. We have to look at the energy from that. And we're not going to get that complicated with things. But just know that the principal quantum number n is some integer number, 1, 2, 3, or so on. The second part of the address is the angular momentum quantum number. Okay, angular momentum basically means spinning around, going in a circle. This is which orbital it's in. Is it S, P, D, F, G, and so on? And we've talked about all those different orbitals, S, P, D, and F, and so on. These are given values of 0 up through 1 less than the principal quantum number. So L, the angular momentum quantum number, if that's 0, that's an S orbital. If it's 1, it's a P orbital. If it's 2, it's a D orbital. If it's 3, it's an F orbital, and so on. Now remember, the first principal quantum number n is 1, and that only has an S orbital. So if n is 1, L can only be 0, n minus 1. If n is 2, the second level has S and P. Energy level 2 can have L be 0 or 1. Energy level 3 can have SPD, L0, L1, L2. Principal quantum number 4 can have SPDF, or L of 0, L1, L2, L3, and so on. And really, this just indicates the shape of the orbital. S is a sphere, P is a dumbbell. We'll get into that in the next video. The third quantum number is what's called the magnetic quantum number. And this tells you which part of the orbital it's in. So think of what L is. And these numbers can range from positive L to negative L, which includes 0. So if L is 0, meaning it's an S orbital, there's only one place for it to be. Remember, there's only one S orbital. But if we have a P orbital, remember there were 3 pieces to the P orbitals, the 3 orbitals for the P. So there's a PX, PY, PZ along each axis. So that means if L is 1, M can be negative 1, 0, or positive 1. If L is 2, that's a D orbital. Remember, there were 5 different shapes it could be in. I won't go through all of the names of those, but there's 5 different shapes. L is 2, the magnetic quantum number can be negative 2, negative 1, 0, positive 1, or positive 2. All right, they go from negative L to positive L. F sublevel has 7 orbitals. That means L is 3, so we can go from negative 3 to positive 3. And that just tells us which, remember, if we're making the boxes, which of the 7 boxes the electron would be in. The last is the spin quantum number, and that's either plus 1/2 if it's spinning up or minus 1/2 if it's spinning down. Right? Because each Each orbital, each box can hold 2 electrons, one up and one down. And the ones up we call plus 1/2, and ones down we call minus 1/2. And with those 4 numbers, the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number, we can describe any electron that an atom has. Even a huge atom like radon with 86 electrons, we can describe each and every one of those electrons. What main energy level is it in? What sublevel is it in, as P, D, or F? Which orbital within those sublevels is it in? And then is it spinning up or down? Now, we have to stop here and look at the Pauli exclusion principle. And this says that in any atom, no 2 electrons have the same 4 quantum numbers. Because, and we talked about this last year, saying that we can't have 2 in the same box spinning the same direction. Well, if they're in the same box, the first 3 quantum numbers are the same. And if they're both spinning the same direction, that means their 4th number is the same. So if there's 2 in the same box, they have to be opposite direction spinning. One spinning up, plus 1/2, one spinning down, minus 1/2. That gives them a different 4th quantum number. Okay, we can't have the same spin in the same box. And there's lots of really theoretical, physicsy reasons for that. And if you are really interested, you can look it up on YouTube. But we're not going to get into that. That's quantum physics, not quantum chemistry. So we're not going to worry about that too much here. But the Pauli exclusion principle, exclusion, because it will exclude those electrons. If there's another electron trying to be in the same box with the same spin, it will exclude that electron. That's why it's the exclusion principle. It won't let it sit in the same bus seat.